So here we have an unrooted tree structure, similar to the unrooted trees that we've just been talking about. And it has a sort of funny property here. You'll notice that we have, for example, sequences A and C that are actually, let's say for the purposes of argument, closer to each other in distance. In other words, the sum of that path is a shorter distance than certainly that path, or say that path. So actually, delta AC be the minimum distance out of all possible pairwise distances in this tree. So the question then is how this structure would relate to the actual evolution of these sequences. So the first aspect is this funny property that we appear to have a much shorter distance going from A to C than actually between our purported neighbors. I mean, in this diagram, A and B are claimed to be neighbors, right? Because they're connected by a single internal node. Would this suggest that the tree construction algorithm, whatever tree construction algorithm is used, has made an error in representing the actual evolutionary history of these sequences? That's the first question. The second question is, does the fact that the tree algorithm has placed these two sequences as neighbors, in other words, connected by a single internal node, does that have any valid evolutionary meaning? What does it mean evolutionarily if it has any valid meaning? Any question about what you're being asked? Okay, so I think if you log in the usual way, you should see this question. So, a couple comments on this. The first is that it's certainly a valid unrooted tree in the sense that there's nothing about this tree that implies that an error was made in the reconstruction of the tree. You know, something that I've been trying to emphasize throughout this whole analysis of additive distances is that, you know, the length of any given edge can't really be treated as having kind of a rigid meaning with respect to everything else in the tree. Basically because under additive distance assumption, we allow for the possibility that the mutational rate could actually be different during different periods of time, which would basically be, you know, you can take a given edge and stretch it or shrink it, and it doesn't change the topology of the tree. The algorithm should recover the same topology regardless of how much you stretch or shrink any given edge, independent of the other edges. So it is certainly possible that, you know, the mutation rate might have been very low here, so that this might actually be a really long period of time, but it shows up as a short distance within the tree, whereas this might have actually been a much shorter period of time, but maybe the mutation rate was much higher then, so it looks like a longer distance, okay? So when we drop the ultrametric distance assumption, the molecular clock assumption, sometimes called, we no longer interpret distance as being, you know, strictly related to time. You can do all sorts of stretching and shrinking, and you have to kind of bear in mind that what matters is topology, basically, in the interpretation of what you're seeing. Okay, so the second aspect is, does the fact that we're directly connecting A and B with a single node have meaning, tell us something about the evolution of these sequences? And the answer is yes, it does, but that evolutionary meaning can be a bit subtle. One way of thinking about and understanding that the subtlety of what it's telling us about the evolution of these sequences is to think about the whole question of the location of the most recent common ancestor. As we emphasized, I think, when first introducing unrooted trees, the unrooted tree doesn't tell you where the root is. Strictly speaking, it could be anywhere on this tree. That is to say, at any location along any of these edges, we could say, oh, the most recent common ancestor, the root of the entire set of sequences in the tree, is right there. It's possible, right? Maybe the mutation rate was really, really slow there, and it was much faster, everywhere else. That's at least possible in principle under the relaxed assumptions of additive distance, which basically has a direct correspondence to sort of the unrooted tree representation. Don't try to pick where the location of the root is. So when we take into account this idea that the MRCA could be lots of different places on this tree, you can see evolutionary meaning in the precise connectivity, but it might not be exactly what you thought it was. So, for example, when we look at this set of three sequences, can we say that A branched from B more recently than it did from, say, C? You're shaking your head. What's your reasoning?
Because the distance is taken into account the mutation rate and the time, so we can't just talk about the time. Because it might be that the long edge is having a fast mutation rate.
Right. But now, let's say we do want to talk about time and ask the question about, I guess what you might think of as kind of the branching order. There was let's say, clearly there is a most recent common ancestor of all three of these sequences, A, B, C, somewhere. And then there's some branching events that occur that produce A, B, C. So the question is, does the fact that A and B are connected in this way imply that basically A branched from C longer ago than, say, branched from B? Sorry? You're saying yes, it implies that? Well, so we can try to assess that by considering the possible MRCA locations. Okay. So if we, for example, placed let's see. If we were to place the MRCA for all three sequences right there, then that would imply that all three of them branched at exactly equal time from each other, right? If we place the MRCA right at that triple junction. Whereas if we placed it here, the implication would be that B and C branched from each other more recently than they did from A. Because if that's the MRCA of all three of them, then you can think of that as being like the root of that tree of three sequences. So we would draw one long period of time going down to A, then a period of time going down to the ancestor of B and C, and then a shorter period of time going down to B and C from their common ancestor. Whereas if we were to place it over here, the implication would be actually that A and C branched more recently from each other than they did from B. And if we replace the MRCA for all three of them over here, it would imply that A and B branched more recently from each other than they did from C. So the clear conclusion from that analysis of all the places you could put the MRCA for those three sequences says, well, having seen this unrooted tree, we still really don't know whether A and B branched from each other more recently than they did from C, which would sort of make it start to feel like, well, gee, is there any evolutionary meaning to the fact that we're making them neighbors in this diagram? There is meaning. So now I'm gonna try to say it as simply as I can. The key is this extra edge that goes across here over to this side of the tree as opposed to that side of the tree. Basically what it's saying is there is an extra piece of evolutionary history connecting everything on this side to everything on this side. Okay? So one way of saying that is, say I have just one sequence right there, okay? Then there's basically three ways of pairing these up, right? If I pair A with B, then I get those two paired and those two paired, okay? So you can imagine, what if I sum the distances for the possible pairs when I consider the three possible ways of pairing A, either with B, or with C, or with D. So I'll get that sum of distance, which does not include that edge. If I pair A with D, I'll have that, and I'll have that, which now does traverse this edge twice, once in each pair. And then if I pair A with C, I'll get that plus that, which again includes this extra edge twice, one in each pair. So the point is, if you choose the pairs actually to be neighbors, the sum of the pairwise distances will be less than any of the other possible pairings in which they're not neighbors. It's basically saying there's an extra piece of evolutionary history connecting the non-neighbors. What is that extra piece of evolutionary history? It's that period right there. Okay? So we don't know where this MRCA is, but basically there's an extra piece of history that connects this group and that group that you don't have to traverse if you just consider the neighbors themselves. Okay? That's the simplest way of saying it. It's also actually a test. What I just stated is a test for the additive distance assumption. That is to say, for any group of 4 sequences on an additive distance, under the additive distance assumption, if you take the 3 possible pairings of the sequences and you sum the distances of the pairs, 2 of those pairings should be equal, basically because they sum up the same set of edges, and they should, the third possible pairing must be have a smaller sum of distances than the other two possible pairings. Why? Because that's the one where the pairings are actually the neighbors, and therefore it doesn't include this extra piece of evolutionary history. Okay? So that's sometimes I think called the 4-point test for an additive distance assumption. You basically test whether your distances really obey the additive distance assumption by checking it on all possible groups of four sequences. Questions?
So I'm a little bit confused as to the notation here versus the previous slides. Right? On the previous one, you had delta of AB equals 0, and here you have clearly delta AB is.
So I should emphasize, in the previous slide, I said there were lots of other edges that contribute to these Q. Okay? So this is only considering gamma edge and delta edge. There's lots of other edges that contribute to Q. I said we're going to ignore them in this analysis because the same arguments apply to them also. Either they are on path or they're not on path, and the exact same analysis would apply. We also didn't consider external edges, which clearly contribute to the distance from A to B, because the power from A to B only consists of external edges. Yeah, my apologies for inconsistencies in the lettering. Question? Maybe it'll help if I just redraw this very, very simply here. So let's just consider the simplest possible tree structure. In any tree, we can always, for 4 sequences, we can pick out some structure and it'll reduce to this. So basically A, B, C, D. Okay? So I'm going to call these alpha, beta, gamma, delta, epsilon. So if you look at the possible sums, basically the distance delta is the distance from one sequence to the other. What do you want to call it? Want capital D? Okay.
Zeta.
Well, I want something simple here. I'm just going to call it F for some function that. So the simplest way of seeing this is that this pairing pairs the neighbors, so it's basically going to be that plus that, whereas the AC basically traverses like this plus this. So you can see the alpha and beta edges, gamma and delta edges, the external edges are included in both sums, right? Whereas the internal edge is not included in the case where you pair the neighbors, whereas it is included in the other cases, okay? And then the other one is just flipped around. So instead it's like that. So those two sums are equal, and they're always greater than that sum. So this is a so-called 4-point test for additive distances. Did I answer the question? Question? It's a way of testing whether the pairwise distances that you're given or which you compute actually seem to obey additivity or not. I mean, for any set of 4 sequences, 2 of the possible pairings, the distances should sum up to approximately equal. And you could imagine constructing some kind of p-value test for assessing whether the slight, whatever deviation you see, falls within the range of noise that you would expect. And if it doesn't, you might reject additivity and say either this matrix is the wrong matrix for the data that we're working with, or they don't really obey additivity, or something is wrong. So we won't believe the trees that we get built on these distances. Because the neighbor joining, it depends on additivity. Additivity, if the distances actually aren't additive, then neighbor joining no longer guaranteed to work. Other questions?